All right, these are your notes on dihybrid cross Punnett squares. A dihybrid cross Punnett square takes the skill that you already have in a simple Punnett square and adds another wrinkle to it. We'll be looking at two characteristics rather than just one with a dihybrid cross. And here is your example problem. We're going to cross a heterozygous tall brown male individual with a heterozygous tall brown female individual. The way I always set these problems up is I write the genotype of the parents above them so that I can use the genotype later. So in this case, if I'm talking about a heterozygous tall and brown male, to be heterozygous tall, you are big T, little t. Hetero being different, tall being as long as you have the big T, you're tall. And a heterozygous brown individual with a big B and a little b. Heterozygous, but still brown because you have the one dominant allele. Then I'll write the same genotype for the mom because she happens to be the same. She is heterozygous tall and heterozygous brown. So we write our male parent up top and our female parent along the side. Now, just to give you a visual, this is how much space your notes are going to take up. So it'll be a significant amount of notes. You'll only have to do 4 of these problems all semester. So this is one of them. So it takes a lot of space, but we're not going to do many of them. Okay, so here's where we are. So keep in mind, you need to draw your grid large enough to fit 4 letters in each cell. So it needs to be a fairly large grid. Maybe each one of these is only 1 line, but maybe it's 3/4 the width of your paper so that you can clearly write everything in there. So now we're going to use FOIL. And just a reminder, FOIL is actually an acronym, and it's first, outside, inside, last. And that's telling us how we multiply these groups of letters together in order to get what goes above each square and beside each square in order to combine them in the middle, like we do here. It's much easier here. You just take the alleles and write them above. Here we have to use FOIL. And here's how it works. The first of each of my pairs of letters, the first T is a big T, the first B is a big B. So my first is big T, big B. The outside of all 4, the outside on one side is a big T, the outside on the other side is a little b, so my outside is big T, big B. Sorry about the yellow. I'm going to correct that right now, and I'm going to make it purple. No, oops, let's do this. So here's my outside, big T, little b. Okay, then next I look to the inside letters. What's inside is a little t and a big B, so I do little t, big B. And then I look to what's last in each pairing. The last of the t's is little, the last of the b's is little. So little t, little b. Okay, now I have one set. I have to do the same thing for this parent. Fortunately, because the parents are the exact same, their combinations will work out the exact same. So I'm going to do it a little faster now. First is a big T. The first of the B's is a big B. Oh, whoops. At some point in time, we're also going to talk about genotypic and phenotypic ratios, so you will need to write that. I'll give you a moment to write that. All right, so the first there is big T, big B. The outside, big T, little b. Oops. I'm going to redo that color as well. It is. I already said that. I'm just saying for people who want to see the FOIL done one more time, I'm going to do it quickly. Little t, big B will be the inside, and little t, little b will be last. Because the parents are identical, the way they can distribute their alleles is identical. Now we cross them. The way we cross them is a big T drops down there in this column. A big T goes across in that row, so we have big T, big T. You always write the letters together. You wouldn't write big T, big B, big T, big B. It just gets too convoluted that way. You keep the letters together, and then it's big B for the same reason. This big B drops down, this big B moves across. All right, then a big T drops down, a big T moves across. A big B drops down, but a little b moves across. Now a big T drops down. Big T's will always drop down there, and a little t moves across. A big B drops down, and a big B moves across. Last one. A big T drops down, a little t moves across. A big B drops down, a little b moves across. I'm going to give you about 3 minutes to fill this out the rest of the way on your own, and then I'll project the answers.
Do we have to write it from left to right, or can we write it below?
I'm going to say all that again. All right, so genotypic and phenotypic ratios, the way those work is that you're going to tell me how many children will have a particular genotype and how many will have a particular phenotype. The way you do that is I always start in the top left corner with that genotype and slowly work my way across so that I don't miss anything. So the top left-hand corner, the genotype is big T, big B, big B. And I see only one individual that meets that criteria. This top one, big T, big B, big B. Once I find them, I cross them off, and I write 1 out of 16. There are 16 boxes, so we're assuming there are 16 children, at least for probability's sake.
Should we cross them off too?
I always cross the box off so that my brain doesn't have to process whether or not I've checked that box for the remaining genotypic ratios. So I always cross that box off. Yeah, Ben?
So does that mean you can like extract?
All right, next up I'm going to look at big T, big B, little b, because it happens to be the next one on my list. And as I look, I find that I have 2 individuals that are big T, big B, little b. And so I cross them off from my Punnett square, and I move on to the next. Remember that when you're checking, you might have to do more scanning to ensure, but I've worked this problem 3 times now, so I'm very confident that those are the only 2. Okay, next one on the list is big T, little b. I just picked this one to be the next on my list. And as I scan, that is the only cell that has big T, big B, little b. So this again is a 1 out of 16. Only 1 out of their 16 children has the chance of being homozygous tall and homozygous white, is what that's saying. Next up, I pick big T, big B. Only 2 out of 16 fall into that category. There is a very nice symmetry that occurs when your parents are the same alleles. When you have heterozygous tall brown and heterozygous tall brown. So we'll be able to cross these off in a very predictable pattern. The next one on the list is big T, big B, little b, and there are 4. 1, 2, 3, 4 that all match that criteria. And so we'll cross those off so that we don't bother recounting them later. Next one up is big T, little b. And I found just 2. This cell here and this cell here. Next is little t, big B. So the odds of them having a child that is short homozygous and brown homozygous, 1 out of 16. Just this cell here is little t, big B. And so I cross it off. Only 2 different genotypes to go. Little t, big B, little b. There are 2 out of 16. This cell here and this cell here. And finally, there is just 1 left. Little t, little b. Now the phenotypes go faster because several of these fall into the same phenotype. And there are only 4 possible phenotypes. A child could be tall and brown, or a child could be tall and white. A child could be short and brown. A child could be short and white. We happen to have students with the name Brown and White in here. So you can think of tall and brown is Ben. Tall and white is Kylie. Neither of them are particularly short, so those ones don't work. Okay, to be tall, you need at least 1 big T. To be brown, you need at least 1 big B. So here I have at least 1 big T and 1 big B, so that's 1. Here I have at least 1 big T and 1 big B, so that's 2 more for 3. This one doesn't count. Here I have at least 1 big T and 1 big B, so that's 2 more for 5. And here I have at least 1 big T and 1 big B, that's 4 more for 9. In no other do I have at least 1 big T and 1 big B. So to be tall and brown, they have a 9 out of 16 chance of having a tall brown child. So Ben's a 9 out of 16 chance. Tall and white, Kylie. To be tall, you need at least 1 big T. To be white, you need all little b's. So as I look at this, here is at least 1 big T and all little b's. That's 1. So we got 1 Kylie, all little b's. There's at least 1 big T and all little b's. There's 2 more, that's 3. Nowhere else do we have a tall individual. So the chance of having a Kylie is just 3 out of 16. Short and brown, we need little t's and big b's. So we move over here to our little t section. There's 2 little t's and at least 1 big B. That's 1. There's 2 little t's and at least 1 big B. That's 2 more for 3. 3 out of 16. If this is out of 16, what should my numerator add up to? 16 indeed. We have 9 plus 3 is 15. So that must be a 1. That's a way of checking your work. This must be a short white individual. That's all little t's, all little b's. And sure enough, we have only 1 of those. That is a dihybrid cross. You're now going to work